This lecture will be introducing you to the concept of bivariate regression, which is a type of hypothesis testing of the relationship between two interval or ratio variables. We're setting the foundation here for multivariate regression, so it's important to understand these basics, and we'll go deeper into this in the next several lectures. So I'm going to be talking about the logic of what bivariate regression is, and then I'll provide the equation for bivariate regression in this lecture. So first, let's think about the relationship between correlation and regression. So we just talked about the correlation coefficient, which measures the relationship between variables. So how is that different than what we're doing with regression? So again, the correlation coefficient isn't specifying which variable is the dependent variable and which one's the independent variable. It's just saying how do two variables vary together? How much are they're related? But you're not saying that X causes Y. So there's no model of causality that's built into this. So for example, to what degree are years of education and income related? You might say that more education causes higher income, but then you could flip that around, that people with higher income are more likely to get more education. So that's not a problem for the correlation coefficient, the fact that you could have both directions of the causality there. They just want to see how much they go together. This is different than regression. So there's that example there between the years of education and income. Regression, in contrast, does specify which variable is the dependent variable and which one is the independent variable. And it specifies how to quantify the effect of a change of X on Y, right? So you're saying where the line is, how they vary together, and you're saying which one is going to be implicitly your cause. So for example, how much does the additional year of education have on income, right? So you're saying that education is the independent variable and income is the dependent variable. You're asserting a model of causality in which you believe that education causes people to have more money over time. Bivariate regression is is known as part of linear regression. And that simply means that it's following the formula for a line, right? Y equals mx plus b. That's the old equation that you had in middle school for the formula for a line. So just looking at this, draw your quadrants there and draw the line. We're going to go through the different pieces. So here is b, and that's the intercept, right? So there, and this is where it's intercepting with the y-intercept, okay? And m is the slope, right? It's how much this is right here, right? As you go over one, how much do you go up? So it's the same exact thing as for a line, just applied for a different application than you had when you were first learning algebra. So here is the equation for bivariate regression. It's pretty much the same thing as what we just saw on the last page, more or less. So the equation for a regression line in general is y, our dependent variable, equals alpha, and that's the constant or the intercept, okay, the y-intercept, plus beta times x. So beta there is the slope. And here's where it's slightly different, which is that you have a residual random error. Remember those scatter plots that I showed you? In general, a lot of the observations weren't exactly on the line. And so that means that you're going to have some variation in there randomly. If you were to average it all out, it would simply be this piece here. If you're talking about individual data points, this is the equation, right? So you're going to have some variance, and that's what this is doing. This is called the residual, and it's an element of random error. So just to repeat this over again, this is the exact line, right? This is the thing that we definitely will know. And this is the residual, which follows a normal distribution. It's our error term, okay? So you don't ever actually calculate what this residual is per se. It's just explaining how it's going to be different from the equation that we developed for a line. So thinking through this with an example, imagine that you are doing a study that looks at the rates of participation in civic organizations and civil society groups, and how that affects voter turnout. So you're arguing that when a country has a high level of participation in these organizations, they're going to have higher voter turnout overall. So here are your data points. So imagine this is a bunch of countries, and you want to look at what the regression line is. You see that it is a positive relationship. It's going up. Okay, that's good. And what is the line that fits this? So if you were doing a more advanced statistics class, you would go through and figure out how to derive this line, which is called ordinary least squares. We'll just skip over that. So the equation that you can come up with here is that y equals 30 plus 1.3x plus the residual. So thinking about this, that means that it intercepts right around here. So if you were to have a country that had no participation in a civic organization, you would estimate that they would have a 30% turnout rate. That's what that means. I don't have any data points here because that's really not something that you ever see in a democracy, but it's possible, right? And then as you're increasing, basically for every 1% increase in participation in the population, you're going to see a 1.3% increase in voter turnout. So that's what we're capturing here, right? Go over 1 here, go up 1.3. Over 1, up 1.3. And this residual here is how to explain data points like this and this and this and this and this that don't fall exactly on the line. So this is what we would expect, and these data, that's what we actually have in real life. So in future lectures, we're going to talk about how to interpret outputs that we get from this and how to incorporate probability into our discussion of regression.